Hi there, I'm Keke, and this rather odd-looking machine over here is called the Van der Graaf generator. In today's lesson, we are going to use this machine to learn more about charged objects. By the end of this lesson, you should be able to explain how to identify the type of charge on an object and describe how charged objects affect one another. Let's start by finding out how the Van der Graaf generator works. A broad belt in the middle of the machine rotates around a wheel. As the belt moves past a metallic brush at the bottom of the column, it becomes positively charged because it loses electrons to the brush. The positively charged belt now moves upwards as it passes the upper brush. Negative charges move from the dome and brush onto the belt to neutralize the positive charges. This means that there are more positive charges left behind on the brush and metal dome than negative charges. So the metal dome is now positively charged. The longer the machine is left to run, the more positive charges there will be on the metal dome. Now, we were lucky enough to get permission to film this machine's big brother at the Wits University Physics Department. Have a look at this demonstration. Letitia is standing on a plastic insulator. This will prevent any charges from the generator passing to Earth. This means that the charges accumulating on the metal dome will also accumulate on Letitia. Letitia is standing with both her hands on the metal dome. Do you see how her hair is standing on end? As she becomes charged, her hair rises slowly up into the air until it is sticking out in all directions. Can you explain why this happens? Because Letitia is touching the metal dome, negative charges move from her body onto the metal dome to neutralize the positive charges. Positive charges are therefore left behind on her body. This also includes the hairs on her head. All the hairs will have the same charge and they will repel one another and move apart. The scalp also has the same charge, and so the hairs move away from it up into the air. So what have we learned from this demonstration? Each strand of Letitia's hair carried the same charge, and there was a force of repulsion between the strands. So it seems that objects with the same charges repel each other. That's quite similar to what we learned about magnets. In our lessons on magnetism, we showed that like poles of magnets repelled each other, and opposite poles attracted each other. Let's see if we can establish a similar rule for static electricity. The first step we need to take is to find a way to detect the kind of charge that an object has. We can do this using an instrument called an electroscope. I have an electroscope here in front of me. This is a gold leaf electroscope which has been manufactured, but you can make a simple foil electroscope at home. Instructions on how to make an electroscope can be found in the Mindset print material available on our website at www.mindset.co.za. You can use an electroscope to detect the presence of charge. They can also be used to determine the type of charge on an object. This means that they show us whether an object is positively charged or negatively charged. An electroscope is neutral to start with. We can charge it using an object which has a known charge. For example, when I rub this comb with nylon, I know that it will become negatively charged. Watch what happens when I rub the negatively charged comb against the metal cap of the electroscope. When the negatively charged comb is rubbed against the metal cap of the electroscope, the negative charges or electrons move onto the metal cap. When the comb is removed, the negative charges distribute themselves evenly and the electroscope is now negatively charged. In a charged electroscope, the two leaves stand apart from each other. The negative charges are equally distributed throughout the metal parts of the electroscope. This includes both of the leaves. As both leaves are negatively charged, they will repel each other. Now, let's see how this negatively charged electroscope can be used to detect the type of charge on an object. If I bring a negatively charged object, for example the comb that was rubbed with nylon, near to the metal cap of the electroscope, what happens to the leaves of the electroscope? Why don't you try and provide an explanation for what you've just seen? Did you see that the leaves of the electroscope moved further apart? The negative charges on the comb repelled the negative charges on the cap of the electroscope. Negatively charged electrons can move, and they moved from the cap into the leaves. A greater negative charge in the leaves means a greater force of repulsion, and the leaves moved further apart. If I now bring a positively charged object, for example a glass rod rubbed with a silk cloth, near to the metal cap of the electroscope, what do you think will happen to the leaves of the electroscope? Let's have a look. Do you see that the leaves of the electroscope move nearer to each other? The positive charges on the rod attract negative charges. Negatively charged electrons move from the leaves up into the metal cap. There are now fewer negative charges in the leaves. There is therefore a smaller force of repulsion, and so the leaves move closer to one another. If a charged object causes the leaves of a negatively charged electroscope to move further apart, the object is negatively charged. If a charged object causes the leaves of a negatively charged electroscope to move nearer to one another, the object is positively charged. Now that we've established how to test the charge of objects, we are ready to test the statement, opposite charges attract and like charges repel. I will need help in this investigation, so I asked Aaron to come into studio. Oh, and here he is.
Hey, Kiki, how are you?
Hi.
Now, I've brought the 2 balloons that you asked me to pick up.
Great. Could you please, because these are going to help us in our investigation, if you can rub that red balloon on the jersey, then check its charge there on the electroscope.
Of course. Let me rub it onto there. Okay. Now check this out. Now see that the leaves of the electroscope are moving further apart from each other. Now this means that the balloon becomes negatively charged.
Now you see, in the meantime, I rubbed this blue balloon with cling wrap. Let's test its charge. This blue balloon is positively charged. I know this because the leaves of the charged electroscope are moving closer to each other. Okay, Aaron, hold your balloon still while I bring it closer to mine.
Look, they attract.
That's right. This is what we were hoping to see. The charges are attracting each other.
Now, what do you think will happen if we give both the balloons the same charge?
Let's see.
Rub it, rub it.
Rub it hard. Think that'll be enough. Let's see what happens.
Okay.
It seems to be quite attracted to you.
Well, they're running away from each other.
Yeah.
They
are.
like each other.
They're pushing, like repelling against each other. That's great. Okay, hello.
That's what you're hoping to see here.
This is... our investigation is going very well. Wow. In this investigation, we proved that oppositely charged balloons attract each other and same charged balloons repel each other. Now this supports our statement that opposite charges attract each other and like charges repel one another. Thanks so much for your help, Aaron.
Sure, sure.
Why don't you guys try this task at home? Draw a series of diagrams to show how a negatively charged electroscope is used to identify a positively and a negatively charged object. Now, in our next lesson, we'll be looking at electric fields and comparing them to magnetic fields. But until then, goodbye.
Chap, chap.